there is a point. And through that point, everything becomes its opposite. In the last 2 episodes, we explored what symmetry looks like when you rotate and when you mirror. But there is a third operation. It needs no axis, no plane, only a single point. Let us start with what we already know. Take one hand. Rotation. We spin at 180 degrees around an axis. A right hand becomes still a right hand. Handedness is preserved. Mirror symmetry. We reflect across a plane. Now we have 2 hands, but they face each other. You can superimpose them. A right hand has become a left hand. Now, pause for a moment. What else could you do with this hand to generate a new, symmetrically related position? Think about it. Flip it upside down. That is still a rotation. Still a proper symmetry operation. Handedness has not changed. Move it sideways. That is translation, and in point group symmetry, translation is not allowed. We are studying operations that leave at least one point fixed. What if you pass the hand through a single point? Try this right now with your own hands. Hold both hands up facing each other, as if about to clap. Now flip one of them upside down. That is what inversion does. A right hand, palm toward the center, fingers up, becomes a left hand, palm toward the center, fingers down. Rotation could not do this. A mirror plane alone could not do this. Only inversion. Every single point of the object, every atom, every vertex, travels in a straight line through the inversion center and reemerges on the exact opposite side. Same distance from the center. Exactly opposite direction. In coordinates, the rule is elegant and total. Every point, x, y, z, maps to -x, -y, -z. All 3 components flip signs simultaneously. That is why we need a point, not a plane, not an axis, to anchor this operation. Rotation needs an axis. Mirror needs a plane. Inversion needs only a point, a single location in space through which the entire structure finds its counterpart. Like mirror, inversion changes handedness. The result is a left hand, and no rotation in 3 dimensions can turn a left hand into a right hand. This is why inversion, like mirror, is called an improper symmetry operation. Mirror and inversion both change handedness, so it is tempting to treat them as the same thing. But they are fundamentally different. Mirror operates across a plane. It is essentially a 2-dimensional operation extended into 3 dimensions. Inversion operates through a single point. It is inherently, irreducibly 3-dimensional. You cannot describe inversion with a mirror plane. Before we enter the crystal, there is something important to establish. The mirror plane we drew in episode 3 does not physically exist inside a crystal. The rotation axis does not exist. The inversion center does not exist, not as real objects embedded in the material. What exists are atoms. And some of those atoms are related to each other by symmetry. They are equivalent positions in the structure. The mirror plane, the rotation axis, the inversion center, these are mathematical descriptors. Convenient, powerful ways of stating those equivalence relationships precisely. They are the language of group theory, which gives us a rigorous and complete framework for describing the geometry of crystals. Group theory works so elegantly here because the set of all symmetry operations of any crystal forms a mathematical group, and it turns out there are only a finite number of such groups possible in 3 dimensions. When we say a crystal has an inversion center, we mean, for every atom at position x, y, z, there is an equivalent atom at -x, -y, -z. The point is a description of that relationship, not a physical object. With that grounding in place, let us look at what these relationships mean for real crystals and for the physical properties that emerge from them. Some crystal structures possess an inversion center. We call them centrosymmetric. Others do not. This single distinction determines whether certain remarkable physical properties can exist in a material. Non-centrosymmetric crystals can exhibit piezoelectricity, generating electric charge when mechanical pressure is applied. Some also exhibit optical activity, rotating the plane of polarized light as it passes through. These properties are strictly forbidden in centrosymmetric crystals. The inversion center cancels them out. Calcite, calcium carbonate, is a beautiful example. Its space group is R3C, which belongs to a centrosymmetric Laueclass. Calcite has an inversion center, and so it does not exhibit piezoelectricity. But quartz, also a carbonate-adjacent silicate, lacks an inversion center, which is exactly why it can be used in piezoelectric devices. Here is something beautiful and surprising. Even when a crystal has no inversion center, its X-ray diffraction pattern almost always looks as if it does. The intensities of the H-K-L reflection and the -H, -K, -L reflection are equal. This is Friedel's law. The physics of diffraction itself adds an inversion center to the pattern, whether or not the crystal has one. Because diffraction always adds an inversion center, every crystal class, when observed through diffraction, collapses into one of only 11 centrosymmetric groups. We call these the 11 Laueclasses. The 32 crystallographic point groups reduce to 11 when viewed through the lens of diffraction. Inversion symmetry is, in a sense, the default language of X-ray diffraction. In crystallographic notation, inversion symmetry is represented by this symbol, I, pronounced bar1 or -1. It means, apply the inversion operation once. The bar over the number is the notation for inversion combined with that fold of rotation, but for bar 1, the rotation is trivial, and we have pure inversion. What happens if you apply inversion twice? You return to exactly where you started. Applying bar 1 twice is the identity operation, nothing changes. Inversion is its own inverse. This is a property it shares with the mirror operation. In future episodes, we will explore what happens when you combine rotation and inversion into a single, simultaneous operation. These are called the roto-inversion axes, and they produce some of the most elegant and counterintuitive symmetry patterns in crystallography. That story is coming soon. Let us gather what we have learned. 3 fundamental symmetry operations, each defined by a different geometric element. Rotation by an axis, mirror by a plane, inversion by a single point. Rotation is proper, it preserves handedness. Mirror and inversion are improper, both change handedness, but through completely different geometric mechanisms. There is something quietly profound about inversion symmetry. A single point in space, and through it, the entire structure finds its counterpart. Every atom balanced by its exact opposite at exactly equal distance on the other side. In the geometry of crystals, as perhaps in broader things, every point has a partner. If this episode helped you see symmetry differently, share it with someone who works with crystals or anyone curious about the hidden order in the world around us. The next episode will explore roto-inversion, where rotation and inversion become one simultaneous operation. Until then, keep looking for symmetry.